Happy Monday everyone, and welcome back to another episode of Rift Amps. Okay, so it's currently Monday, no it's not, it's Tuesday. It's Tuesday. Tuesday afternoon. We've just finished wiring up the PR35 that we've had ongoing. So tomorrow, Wednesday, we'll be able to fire this up, put some valves in it, take some measurements and see how it performs. So hopefully, if I remember, I'll bring you along and show you how we do that, but you can just see how good that looks. So for those that don't know, with the PR range we've got 4 models. We've got the PR6, which, as the name suggests, is a 6-watter. We've got the 18, the 35, which this one is, and then we do a 50 as well. Now, the 18, 35, and 50s all come with a half power switch. The 6 doesn't. But there you go. So that's the PR35 that Jamie's just finished wiring up, ready for testing. Okay, over to the Cornell. Now this one's very interesting because the output transformer still isn't here yet, so I've been because I haven't got a schematic, I'm having to reverse engineer and just work out exactly what's going on, because it's very unusual that the input signal to the grids, as I showed you in last week's video, that input signal changes when you plug the output valves in. Now this amp doesn't have, I was thinking about it, and actually this amp doesn't have negative feedback, so there's no reason why the signal would do that, because it doesn't feed back, but actually it does. And this is very unusual. I don't know if you can see on the board here, we've got this black rectangular block, and it's epoxied in place. Now these boards from Cornell, they actually kind of lacquer them, so it's very difficult to take measurements and to work out what things are connected where. So I've had to pull the board, and actually on the back, hopefully you can see, there's actually a couple of PCB traces on the back of the board, which is very interesting. Now, when I was doing measurements before, I noticed that the cathode resistors, for the output valves, they go straight to ground, but the bypass caps do not. And I couldn't find where, at least measuring from the top, where they were connected to and how the thing works, but I found it. These two caps join together and then come into this terminal here, into this block. This leg is grounded, but these two legs, both on underside traces, come to the output of the phase inverter, which then go to the grids of our output valves. So that's our feedback loop. Very interesting that he's done it off the cathodes, but whatever is in here clearly is where our fault lies, and it's not the output transformer. This is something I've never come across before. I've never seen it. Very interesting. So I've got to I've tested these caps just while I was, that's why I've lifted the legs. We tested those caps. They're okay, they're good, everything measures in spec. So our feedback issue has to be in this box. Now I couldn't get hold of Cornell today, so I'm going to try again tomorrow, Wednesday, and see if we can get an answer as to what's going on in here and why it's affecting our signal. I should say, also just check these coupling caps in case there's DC leaking and that's causing the issue, but we'll see. But yeah, I've had to pull this board out partially to actually work out what on earth is going on. Right, so I've got something quite special for you. Yesterday, a customer dropped in his 1978 Marshall 2203 JMP 100 watt head. This is the one that everyone wants, along with the 50. He's brought it in just for a simple revalve. He supplied the valves himself, so all he's asked me to do is just to install them, check and set the bias, and give it a soak test. So that's what I've done. So here we are. This is a November 1978 model. Vertical input, master volume 2203. So I thought I'd just explain to you how I like to bias amplifiers up. Lots of different methods of doing it, and most of the time that involves going online, using a calculator, and just setting the bias to a particular number. Now, I don't like to do that because that number that the calculator spits out might not be the best operating point for that particular amp with that particular set of valves. So I like to bias using a signal generator and an oscilloscope. So we've got the amp, we've got the valves installed, we've got the amp on, and as you can see, as I turn the volume up, we've got an output. Now I've already set this to where I'm happy with it, but essentially what I want to do is, as I look at the rising and falling edge of the sine wave, you can see there's a tiny little step there. That's crossover distortion, and what I like to do is, using a bias screwdriver and with the amp set to roughly its output. Now this is a 100 watt amp, so I'm driving an 8 ohm load, so for around 98, 100 watts or so, we're looking for about 28 and a half volts output. Well, that's currently doing 30 volts, so just bring that down. So that's about 100 watts there. And as you can see, there's a tiny little bit of crossover distortion on there. So I'd just like to go ahead and turn my bias pot just to the point where that smooths out and disappears, which is about there. As you can see, that's now gone. So that's now I've now set the operating point, the bias of the amplifier, to a point where we're getting full conduction from the valves, but we're not overrunning them. There's a lot more adjustment left, so I could run these much hotter. But that's the point on the oscilloscope where it's producing the output it needs to, and it's a nice clean sine wave. So now what I can do is turn the volume down so the amp is now idling, and I can take my measurements. So there's two measurements that I need to take. First one I need to know, and we'll just do this on one valve and then we can go back and check. I need to measure the voltage from the anode or the plate. We'll do this one here, second one in. There's the anode, pin 3, measuring to ground, 470 volts DC. So voltage anode to cathode. Cathode is grounded, 470 volts. Second measurement I need to take is the well, on this amplifier we've got 1 ohm resistors from the cathode to ground, and by measuring across there we get an instant conversion to milliamps. So that, if I measure at that point, we've got 39.9 millivolts. Call it 40. Because it's a 1 ohm resistor, that converts to milliamps, so we can say our current at the cathode is 40 milliamps. So those are the two numbers that I need to calculate the bias. So all we do is 470 volts, because as we know, Ohm's law says voltage is current times resistance, and Joule's law, watts, is voltage times current. So we've got our voltage, and we've got our current, and that will give us our watts. So 470 times You convert that to amps, so 0.040. That's 18.8 watts. The maximum for an EL34 is 25, so we take that number, divide by 25, tells us we're at 75.2%. Okay. Now, as a general rule, and this is just a rule of thumb, it's not an absolute, you want to be operating on an amplifier like this somewhere between 50 and 70%. So we're currently by slightly hot. So I need to go back and just tweak that until I can get that number on all 4 valves below there. And I usually like to be well, anywhere in that range, really. I know on these amps we can usually get, they sound quite good. They sound very good, in fact, at 65, 66% is where they usually end up. But that's how we do it. So I can come back over to the amp, bring my signal back up till I'm doing 100 watts. It's about there. Just going to do the bias adjustment again. This time I'm going to cool it down, so I'm going to add more negative voltage. Just a smidge. So about there. And then I can take my numbers again. Our anode to cathode voltage has gone up to 474, and our cathode current is 33.2. 474 times 0.372 is 17.63%, divided by 25 puts us at exactly 70%. Excellent. So now all we do is I'm going to leave this running with a signal running through it for about an hour. I'll come back, I'll check the measurements again, and if everything is where I want it to be, then we can button the amplifier up and it's ready to go. Okay, so I just wanted to update you on the Cornell Plexi 1820. I've actually fixed it and the customer's already collected it. I didn't have a chance to film the final fix, but I wanted to explain to everyone what the problem was, so you can all understand where we were going with it. So I just want to quickly show you the output, the standard output stage of a cathode bias 2-valve two output valve amplifier. Here's the 2 output valves. Each of them gets an input from the phase inverter, and typically you might find that the 2 cathodes are tied together and they share a common cathode bias resistor and a cathode bias capacitor. That's kind of a standard layout. Now what you can do, if you want to make that output stage respond a bit more like a fixed bias push pull amp, not a lot, but you know, move it in that direction, you can actually split the cathodes and don't tie them together and give each of them their own individual resistor and capacitor. So that's a common upgrade for cathode biased amplifiers. On the Cornell, however, they'd taken it a step further, in that they had given each output valve its own resistor and its own bypass capacitor. However, those 2 capacitors were tied together and they go down to a mystery box. Now you might be laughing, but I'll show you. Here it is. Now this is this was sat right in front of me. It's plain as day. You couldn't miss it on the board. I'd assumed it had another function, but after I had pulled the board in the amp and folded it forward, I could see where this was connected to and what it did. Well, not what it did, I still don't know, but I'll show you. It's obviously got some components inside and it's been epoxied in place, so I can't get into it to know what's inside. But after we realised that the output transformer wasn't the cause of the problems on the Cornell, and we'd fitted new output valves and we'd tested the resistors and capacitors in the cathodes. Now, the resistors and capacitors in that circuit, in the output circuit, the only thing left was this little box. Now, Cornell, quite rightly, wouldn't tell me what's inside or how it works, but he likened it to a Zobel network or a smoothing network, just to help keep the output stage under control. So it does something. I've drawn out the schematic so you can see what's going on, but the two bypass caps are tied together and they go into this mystery box, and the other side is grounded, so that's providing the ground connection for those caps. However, it then splits off and feeds a signal back into the control grids of the output valves. So there's a feedback network going on. Now, what's interesting is that feedback networks are normally negative feedback, but as we all know, the cathode doesn't invert the signal, so we've actually got some type of positive network, positive feedback network going on. So Cornell, I diagnosed that the issue must be with the box, or something relating to this box, and because I don't know what's inside it, I don't know how it works, and Cornell wouldn't tell me, my only option was just to replace it and see if that made any difference. So phone up Cornell, he very kindly agrees to send one out to me, which we installed in the amplifier, and it appeared to fix the issue. Unfortunately, when the amplifier got hot, the issue returned. So we're kind of back to square one. It's not the output valve, it's not the output transformer, and it's not these four components, and it's not this mystery box. So what could be the issue? Well, as you remember earlier on in the video, when we pulled the board forward, we saw actually the underside of the board had some PCB traces, and what I found was that at the tiniest hairline crack in this side, on this connection here, closest to the point where it joins the where it reconnects here, the tiniest hairline crack in that PCB trace. Now, when the amplifier is cold, that crack is open, so that network's not working, but when it comes up to temperature, it obviously remakes that connection, it expands just enough, and then the amplifier starts working as intended. So once I'd spotted that, all I had to do was, rather than try and repair the PCB, I just added a jumper wire on top of the board, just as a secondary function, just as a backup, sorry, and that fixed the amp. So we saved the customer a lot of money, not having to replace the output transformer or fit new valves. We have a saying in this game that it's never a loose connection, but in this time it was. So that's the Cornell all fixed, back to the customer. Of course, we gave it a soak test, so we know it was fine, but that was the issue with the Cornell. Okay, so yesterday, today's Saturday, I've popped in, but yesterday, Friday afternoon, we had a mystery amplifier arrive in the post. So we'll be opening that next week. We can see what's inside. I think I know what it is, but until I open it, I'm not sure. I think it's another repair. But apart from that, that just leaves us to say thank you very much for watching. Once again, please, if you haven't already, click like and subscribe to the channel. It really helps. I am trying to grow this, trying to give you more content so you can see what goes on in the workshop, what we do, how we do things, and the bigger the channel becomes, the more I can do. So have a great weekend, and I'll see you next week.